Okay, so just to evade more controversy, this isn't going to be a talk about a crazy resolution to the information problem. It's just everything that was left from the previous two talks.
I see.
Okay, good. So it's going to be about stuff I wanted to talk yesterday about the entanglement negativity and some stuff I wanted to talk about fixed area states, basically. So let me start by catching up from where we left over yesterday. So we discussed the reflected entropy, in which case we saw that there were some subtleties with the holographic replica trick calculation, and somehow tensor networks were a nice toy model where we could analyze it and learn something about how the replica trick works. So I'm going to do something similar for the entanglement negativity. This is also a replica trick in holography, which has been controversial for a few reasons. And we're going to see how tensor networks motivate some sort of learning for that.
And I'm really sorry, Pratik, to interrupt you at the very outset, but I mean, the basic lesson, just two sentences from yesterday's talk, was that there was this way of computing the reflected entropy?
Yes.
In terms of the cross-section?
Yes.
Which was not always wrong.
Which was
but did it fail at the analog of near phase transitions, or what was the
it definitely does have corrections to phase transitions, but let's say we're even far from phase transitions. Then already at that level, we'd like to prove it in some rough sense, right? Like similar to Lukowitz-Mandelstam. So taking the replica trick, the naive proof that was provided initially was actually wrong because it suffered from this order of limits issue that I talked about yesterday. Because we could only compute the integer moments strictly with the path integral, and then we needed some prescription. There was an analogous problem that existed in the tensor network, and in the tensor network, we looked and found new saddles which resolved that issue. So now
they were, sorry to interrupt, they were replica symmetry breaking.
They weren't, I mean, so they're not strictly replica symmetry breaking, they still preserve replica symmetry, but they're just different from the naive saddles that were written down. It's a slightly different pattern of gluing, it's a different topology. So once you know that, now it becomes, you could, like there's probably similar topologies you could write down in holography as well, which presumably dominate. It's hard to show that, but it makes, I mean, the tensor network picture makes it plausible that that's what happens.
Okay.
And then once you believe that, then the tensor network provides you a prescription to get the reflected entropy out of that, like analogous to Lukowitz-Mandelstam, like at the level of rigorousness of Lukowitz-Mandelstam, which gives you the cross-section. So this is like a slightly better justification of the fact that the reflected entropy is related to the entanglement mesh cross-section, which helped us prove other things about three-party entanglement and things like that. Okay, so it's that was sort of the
thank you so much.
Message. Okay. All right. So we're going to try to do something similar for the entanglement negativity, which is probably a shorter story than what was said yesterday. And then I'd like to go back to what we discussed on the first day, which was fixed area states. And in fixed area states, we discussed sort of the Euclidean construction of these states. But I'd like to also, and we made a connection with the replica trick in random tensor networks. So there was some sense in which these states were related to random tensor networks. So I'd like to dig a little bit deeper into that and talk about what the Lorentzian description or what the space-time description of such states actually looks like. And then finally, I'll comment on going beyond this connection between tensor networks and fixed area states. There are some limitations to this connection, and I'll talk about how we can try to go beyond that. All right. So let's get started with the negativity. So first, let me define what the negativity even means. To define the negativity, we first define the partial transpose. So this operation is something, so let's say you have two parties A and B. So you have a Hilbert space, which is HA tensor HB. Then any operator, it will have some bras and gets in A and B. The partial transpose is something that swaps the bras and gets only on the B side. So it takes I1, J1, I2, J2 to I1, J2, I2, J1. Okay. So it's keeping A fixed and swapping the indices on the B side. When you apply this, so the operator that we'll be interested in is the density matrix. So we take the density matrix rho A, B and apply this partial transpose operation. And that's going to be denoted by this rho A, B with the TB, where we're saying that we're transposing the B indices. When you do this, you get this partially transposed density matrix. Now, partial transpose is not like Hermitian conjugation, right? So it's not, so this new object is not going to be a density matrix. It's not a strictly positive operator. So what you can show is that it's still trace normalized, it's still trace 1, but it can have negative eigenvalues. And in fact, what has been shown is that the presence of these negative eigenvalues is tied to the fact that there's entanglement in a given state between A and B. So remember that for pure states on A and B, the entanglement entropy measured the entanglement between A and B, but let's say you have a mixed state, then there's a lot of different measures of entanglement. And one of the nice ones is this negativity. So you can show that some kind of entanglement has to exist in order for this negativity to show up. There are some kinds of entanglement which aren't captured by this negativity, but if it's non-zero, then you're guaranteed that there's some amount of entanglement.
So sorry, just let me make sure. So the point is, A and B together are not in a pure state, let's say.
Yeah,
then my naive thought would have been, okay, fine, you take the density matrix for A and B and diagonalize it and find all the eigenstates, and it's an incoherent superposition of each of them. So you compute the von Neumann entropy in each of them, add to it the Shannon part, and that's the full sensible bipartite entropy. And
so you mean you're just computing the entropy of rho AB itself?
Yeah.
So that would be the entropy of, that would be the entanglement between AB and everything else.
Oh,
because you can think of it as purifying this.
Okay. No, I meant further bipartiting
between A and B. Okay, good.
But then you're saying that of course that won't be entirely the entanglement between A and B.
Exactly. It's also including the part which is with the other stuff.
Okay.
So you can think of it as partially including classical correltions between the system. And so that's why it's not necessarily.
So the question is, one's been given a impure. A mixed state density matrix, and you want to somehow find how much entanglement there is between A and B.
Between A and B itself, in a mixed.
Okay, and it's not a unique thing.
It's not a unique thing. There's many measures for this, and this is one nice one.
I think the partial transpose operation I'm familiar with in the context of this positive partial transpose criteria.
It is exactly that,
Right. So there, the idea is that if the state is separable, then the partial transpose is a positive operator.
Yes.
Right. So it's criteria. So if you find it to be negative, if you find it to be non-positive, then you are sure that the state is not separable.
That's right. Yes, that's right.
So okay. So this is about, as you also emphasized, it is about existence of negative eigenvalues.
Yeah.
Now, negativity defined in this way, in what sense is it capturing that?
Yeah, so I was going to get to that. So good. So let's just think about, so we know that, so this was the partial transpose, and then negativity is defined by log of the sum of the eigenvalues of lambda I, of this partially transposed density matrix, which I'm referencing as lambda I transpose. So remember that rho AB transpose is still trace normalized. So the sum of eigenvalues is 1. Now suppose all of them were positive, then this would just be 1, and so the log vanishes.
Nice.
But if there are some negative eigenvalues, then you're sort of adding them in modulus, so it's going to be more than 1. And so the log will be a positive number, and so the negativity is counting some amount of entanglement.
If I can come back, just sorry to slow you down, just to the starting point, if you give me an impure density matrix, but the state is clearly bipartite, A and B, I'd say I'll just do distillation. Just how many bell pairs you can extract is my definition.
So,
why do I need
good. So once I've defined this, let me say a few more things. Firstly, there's a simple generalization of this to the Rennies, which is just computing even moments of this partially transposed density matrix, and that's something that gives you what are the even Rennie negativities, and this negativity can be obtained by some analytic continuation of that. So that's a straightforward generalization. Now, related to what you said, so one of the important properties of negativity is that it's monotonic under LOCC. So this was something I was mentioning yesterday, which is if you do any local operation and classical communication, which is say what you're allowed to do in a teleportation protocol or things like that, you cannot increase the amount of entanglement in the sense as measured by negativity. So you can't increase the amount of entanglement, and so negativity is faithful with that. Now, most things that are known to be monotonic under LOCC are actually notoriously hard to compute. So for example, the thing that you said, like the entanglement of distillation, or there are other things like entanglement of purification and so on.
Yeah.
They often involve something like optimizing over all possible purifications or things like that. And they're really hard to compute. The advantage of this thing is it's a very computable thing. It's one of the only known to be LOCC yet computable things. So that's where the significant advantage is.
And what is its connection to the amount of distillation?
I don't think there's a clean thing. For example, what Abhijit was saying, so there are these bound entanglement states which this misses. And so different measures of entanglement will capture like different aspects of. So there are some kinds of entanglement which can be distilled, but maybe not. It's not captured by this, and vice versa. So there's many different characterizations of it. But what this guarantees is that the state won't be separate. It won't be separable in the sense that it's not just classical correlation. There's some amount of entanglement. Yeah.
Is there
It is symmetric between A and B.
Is there a clear operational meaning if it's not distillation, something else which connects directly so that I'm a lowbrow guy, I read Resnick and Halliday.
Yeah.
I only want operational.
Yeah, not that I know of. I don't know if you.
It's what I was saying earlier.
Yeah.
If you don't work with qubits but some other things, then you can distill pairs.
Oh, then you can distill pairs.
Yeah, I will come back to you.
Oh, okay. That'll be, I'm super interested.
Okay, yeah.
Okay.
So something like that.
Okay, thank you.
So it could be that the negativity is 0, but you still have that kind of
Some kind of.
bound, it's called.
Okay. No, I was actually asking the reverse, but please go ahead, which is.
Yeah, you're saying if there is not bound, what does it mean to have not bound entanglement?
Well, then you can just distill it in terms of.
Is it clear that like everything that the negativity captures is distillable?
Yeah.
Okay.
So
Okay.
Yeah.
Everything it captures is this.
that's called free entanglement in all experience.
Okay. Thank you, sir.
Just so I understand,
Yeah.
rho AB is the density matrix of the full system A and B.
Which is in a mixed state, so you can consider like something else that's been traced out. So
Rho, okay, fine.
that's the system. Yeah.
I see. And you want to compute, so instead of computing, let's say, the entanglement spectrum of AB itself,
Okay.
of rho
Yeah.
AB itself, what you're doing is.
Yeah, if you looked at the entanglement spectrum of AB itself, that would tell you what's the entanglement between AB and everything else.
Yes.
Here we're interested in computing the correlations between them. So one thing you could do was suppose you compute like the entanglement spectrum of A and B separately and
So
maybe
trace
compare
out,
them. Yeah, and maybe compare them. What that does is it still captures classical correlations between them. And what we're trying to do is find something that ensures that it's just the quantum entanglement between A and B that's being captured. So this transpose operation, the transpose operation is basically just flipping brass to kets on one of the systems. So we take the state I1, J1, I2, J2 on this AB system, and we just flip J1 and J2. So it's partial transpose for that purpose. That gives you some other operator which is not strictly a density matrix. It's trace normalized, but it can have negative eigenvalues. So it's not a positive definite object. And the thing that's known is that if this thing has negative eigenvalues, then your state is inseparable. So you don't have just classical correlation, there's some amount of quantum entanglement.
And roughly, why is that?
It's a non-trivial thing to show. Oh, is it? Okay.
So first of all, we have to understand what separability is. That's what we are measuring. So, usually for pure states, when we say that it's not entangled, it means that it's product state. But for density matrices, you say that the density matrix is not entangled, not just when it's product state, but it's convex combination, positive coefficient. That means that it's picked out from some classical ensemble.
Yes.
So if the density matrix has the type pi rho times rho sum over I,
Yes.
then that's a separable thing, and then you kind of like discard this kind of thing because it's just a classical mixture of factorized density matrix.
Probability of
right? But now you can see this constraint is a non-trivial one, right? It's a convex thing. So detecting it is difficult, right? As unlike just a product, having a product.
Because the positivity is it.
Because it's a conical thing, right? It's convex cone kind of thing. So that's a difficult part. But nevertheless, you can come up with necessary conditions in a very simple way. So that when that triggers, you can show that this is certainly not the case. So if this is the case, one thing you can immediately see if you transpose that,
Transpose just this, it leaves this intact.
and then rho B transpose also is a density matrix because the full transpose.
So then it will be.
So now it's a rho times density matrix, again it's a density matrix, so the whole thing is positive. So it remains positive.
No, but sorry, even if it's not a dagger, you're saying it's still a density matrix?
Yeah.
Yeah.
So a positive transpose of positive operator is a
It's a
positive
positive operator. Yeah.
Right, so it's a little faster.
Yeah.
After the transpose. So now notice that rho B transpose is a positive operator. Yeah. So when tensored with that,
So
it's
now-
still a positive operator.
So all eigenvalues of this object are still positive.
Because PRs are also positive. Oh, so there you need the transpose.
Yeah, so the important thing was that because it factorized, the transpose only acted on this factor, and then it's still a density.
But note that this is a necessary condition. You could
Yeah.
still have this
Other
eigenvalue
situations.
positive, but a state may not,
Not
be of
like
this form.
this.
Yeah. And so that's the free versus
Yeah.
kind of distinction.
So in quantum field theory stuff, is this entangled negativity UV divergent? Like,
It is UV divergent.
and so then I guess you.
No. Actually, in all examples, I know it's not UV divergent, but I don't know if that's a theorem or something. Like maybe in some situations it is.
I was going to ask you whether there is some hope to formulate it in this language of the meta-data theory or more appropriate in the quantum field theory.
Yeah, I think that should be doable. I don't think it has been done. But maybe it's doable.
But if it's, I mean, especially if it's not.
If it's not UV divergent, you should be able to do that. I'm not 100% sure. All examples I know, it's not UV divergent.
Even if you consider like spatial subregion.
Yeah, even if you consider spatial subregions, like
Sorry, just to ask, so you take the free field theory
yeah,
and you take the Minkowski vacuum
yeah,
and you take the Rindler observer in one half, or you have access. The A and B are left and right.
no, if you do that, you'll end up with the entropy. But what you want to do is take two intervals.
Sorry.
in Minkowski
You divide it into three parts.
Into 3 parts.
And then look at two.
And then look at two of them.
And you're saying there, this will
So-
give a finite answer.
Yeah, so if you take like two separated intervals, it'll give you a finite answer. That kind of makes sense. If you take the limit where they're touching, then there'll be a UV divergence.
Yeah.
Because then it's like
Because you did this here and that there.
yeah, because then like
Because you're getting rid of the short range entanglement with C, that third guy you're not.
yeah, C is sort of regulating the system. Like if you take this limit, then there's a lot of UV entanglement near the edge, and that's going to diverge. So,
Okay, but still it's interesting. If I didn't do the negativity, I would get a UV divergent. Okay.
for the entropy.
For the entropy.
Yeah.
And somehow doing the negativity makes it finite.
Okay.
No, these are different things.
As finite as the entanglement.
No, these are different things you're computing though. The entropy you're computing was the let's say you took one interval, and then you're computing the entanglement between that and its complement. So they have that UV divergence.
Mutual
No,
information.
I meant, okay, so let me make sure. I divide the interval, realign into three parts.
Yeah,
So
so let's-
A, B, C.
let's
I
call it
keep
right
A and B.
B and everything else is C.
And I compute the Feynman entropy of A union B.
Of AU.
That's a terribly divergent.
That's a terribly divergent object because of the entanglement across these.
C, right? Then I thought what you're saying is now don't take A union B, but take the whatever object obtained by doing the partial transpose.
Yes.
Let's call it rho AB T.
Yeah, yeah.
Now I compute I thought the claim was I compute the von Neumann entropy of rho
It's-
AB transpose.
It's not the von Neumann entropy.
Ah.
Like this doesn't have.
That's
Roll of it.
Yeah. I mean, there is a generalization which computes that, but this one is just like the sum of the eigenvalues.
This is measuring the entanglement between A
It's
and
only
B.
between these.
So it's
So there's-
actual information that you should compare.
There's no UV divergent
Okay.
entanglement between these two.
Yes,
That's all we see.
yes, I agree. So as Abhijit says, maybe the correct thing is to compare this negativity with the mutual information.
It's going to actually be related in holography. I tell you that it's actually related to the mutual information.
Okay, so now I appreciate where it's going. Thank you.
But also A and B are separated.
They're
So,
separate.
so there's no chance then of a UV divergence between.
I agree. Yeah.
No, I was just, I didn't understand how they were getting rid of the Higgs.
Yeah.
So yeah, in that sense, it should have like an algebraic.
But wait, but then this question becomes sort of important. They come together.
Yeah,
So they come together. It is divergent.
it should be divergent. Yeah.
And is taking this transpose roughly like performing a CPT on one half of the?
I don't think it's a CPT because
Isn't it CPT that exchanges gets with bras?
transposition in some sense.
Doesn't it also
taking a
Star.
Yeah, doesn't it also have a star?
Star.
That's the thing I'm worried about.
If you, maybe a PT, but something like
A
that.
PT, yeah, maybe something like that.
I'm very bad with these things, but some operation like that.
Some operation like that.
So if that's the case, it feels like there should be a divergence with these to come together, because then you get that.
Maybe that's one way of thinking about it.
It's an interesting call. If you're basically performing a symmetry,
I think it depends on how you take the limit, because it's roughly like the mutual information, and the mutual information is UV finite for arbitrarily close intervals. It's sort of regulating out that small piece. So,
can you give a Lagrangian? How do you do this in a Lagrangian? What?
in the replica trick?
In a replica trick?
That's very, yeah.
Yeah.
That doesn't involve the transpose. I mean,
Yeah, I
that's
was going to get to the replica trick.
more
but,
straightforward kind
Yeah,
of.
maybe
I mean, yeah.
it's similar, like it's a replica trick similar to the entropy. Like,
I was
slightly
thinking, following Shiraz, that you would take, for the ket or whatever, of the
Yeah.
P part, you would replace it like the
Up and down.
It's up and down.
identifications.
basically that.
Yeah, okay, that's what you do.
Yeah,
Yeah, that sounds right.
that's right.
Yeah. But I mean, one can express it as a more vanilla
Oh, really?
with permutation elements.
Yeah, I mean that permutation element basically does this operation of like flipping the percentages.
Yeah. So if you're effectively changing time, I was thinking something that's going here, moving this way, starts moving that way. That was a
Think
shortcut
of it as
center.
yeah, I guess it's like time loop.
Or not. Anyway, please go on. It's not.
Yeah. Yeah. I mean, even if you took, as long as you took this limit of having two intervals and then taking them closer, it would still get regulated by the fact that there was some small region in between, and this thing is cancelling out that divergence. So even though it seems like,
Yeah, that's fine. Yeah.
This thing, maybe I can also make an initial comment. So this kind of measure is very limited to bipartite systems.
as opposed to more parties.
As opposed to multipartite being mixed states,
Yeah.
let's say. So there also one can ask more refined separability questions. Can a state be written as convex combination of product of three things?
Yeah.
And such. So there are examples where under any bipartition it is separable, but not under the full tripartition.
I see.
So these things are not accessible.
I see. Yeah, this is pretty much a bipartite, like it's a useful measure for mixed bipartites. Okay, good. So that's what the negativity is. Now let me tell you about holography. So there's a replica trick calculation for this, which I'll discuss a little bit. So in holography, there's been a controversy about what really the dual to the entanglement negativity is.
Just one more.
Yeah.
Suppose you did star instead, dagger instead of star.
Dagger instead of this, then it's always a positive operator.
Oh, I see.
I mean, even for partial, let's see. So I'm sorry, I was just talking about this example, but maybe also more generally. I actually don't know. Do you know?
No.
I suspect it's, yeah. The fact that no one computes that suggests that it's not useful, but I actually don't know if it's actually possible.
Thank you.
I thought you can always write the second half as a linear combination of Hermitian units. It's not positive. So once you
What's
take the
the second
second, if you write any state, any entangled state, and you take dagger of the second half, you can write this entangled state as a linear combination of some matrices, right? Some Rho tensor Rho J, but sorry, Rho tensor Rho B, but Rho B need not be positive. It can have negative components. I mean, the state that you have written.
You're not talking about this separable state in particular?
I'm not talking about this state.
Okay.
But still, I think any state can be written as a linear combination of matrices, product matrices. But the second can have negative eigenvalues. And once you take the dagger, you'll get the same Hermitian matrix. So I think just taking the dagger, you'll land up in the same state.
The same second
Yeah.
Saying the full eigenvalue is technically the same.
I guess.
That sounds that does not sound.
Because, I mean, you should.
I didn't understand.
So I'm saying just write a state as a linear combination of
So we can write rho as a sum over what?
some alpha I
The alpha
is lower.
alpha is a real?
Alpha is a real. Some row tensor row delta, let's say.
And this is on A and this is on B, or what?
This is on A and this is on B.
Rho I tensor rho.
The rows are not.
This row delta is not positive.
None of these are positive, right? These are not
They
density
are not
matrices.
positive.
Yes.
Sorry?
If all of them are positive, then you are writing a separate.
That's right.
But
But you can always write it, so let me call it something else, maybe M or something.
yeah,
That's right.
yeah.
M delta. Yeah, okay.
And mi tell that.
Yeah,
And
and
I
this
imagine-
forms the basis, right? In some sense.
Uh,
You can write any
Oh, yeah,
state
yeah.
as a real number.
Yeah, good.
And if you take the transpose, the dagger of mi tilde,
Yeah.
and if this is Hermitian,
It has the same eigenvalues.
it has the same eigenvalues.
But is it
Sorry, why are we
guaranteed
first of all?
to be
But I mean,
I
you
guess
can
it has to
choose
be-
a basis which
Yeah.
in which all of these
It's a
products are
Hermitian
equal,
basis.
right?
So
Yeah.
we can
But then our alpha is real.
Yeah, I think this should be. Sounds right. Because I mean, this is a Hermitian object, so you only ever need the need a Hermitian basis with real components.
Yeah.
Oh no, not with real components. Sorry. No, yeah, with real components. I think you're right. Yeah.
No, but nevertheless, you cannot say anything about
With real, but not necessarily positive, right? Not necessarily
If I take the
positive.
dagger of the second tower, I get the same vector. I get the same vector. So I get the same state.
So if
Saying rho won't change under partial diagram of P.
rho won't change as the partial diagram of P.
Yeah.
P is
Or rho itself doesn't change.
Doesn't
I
change,
see.
so you
I
don't
see.
get
Rho
something.
won't change. Right.
So you will get the same eigenvalues for rho.
Just rho
I
is
see.
not going to
I
change
see.
under
I
that, so
see.
it's not a useful thing to.
I see.
But transpose will change.
Transpose change. Okay, good. So you don't need anything about alpha, except that it's real.
Yeah, it's real and M should be Hermitian.
Yeah. M should be Hermitian. Yeah, good. Yeah, thanks. I think that's right.
Yeah.
Nice. Okay, so good. So holographically, I mean, since this is an actual measure of bipartite entanglement, like one of the most well-studied ones, it's a natural question of what the holographic dual is, right? You'd expect something like a Ryuta-Kinagi formula or something like that. Now, the controversy has been, so there's a simple replica trick, and the replica trick is, I mean, essentially, so when we compute the entropy, let's say you're computing the entropy for two intervals, then what we do is apply, so this is A and this is B. Let's say if you're just computing the entropy of A union B, then you would apply twist operators, which are like twist operator with n, twist operator with minus n, twist operator with n, twist operator with minus n, something like that. And here, just because of the transpose, all it does is swaps these, and this becomes a minus n and this becomes an n. Effectively, that's what ends up happening. So it's a simple CFT calculation that you can write down, and you'd hope to know the answer to this. The CFT answer is actually so when we compute the entanglement, so let's first compute the entanglement entropy. So in the entanglement entropy, what we usually say is there are basically two channels that could dominate. One which is the vacuum block when you fuse these together. So that gives you something of this sort. Or the opposite channel, which is the one which gives you the connected surface. Right? So there's these two different channels, and Hartman and people showed us how exactly this computes the entanglement entropy. Now, if you change these to minus n and n, what ends up happening is, and we can also work in a limit where you're taking these operators to be close enough so that they're in the connected phase. Then the naive channel that you can write down is the following. It has these two fusing, but now you see that the total twist number is not 0, so the vacuum, it doesn't exist in this channel. But there's some other lower operator, which is usually called, I don't know, sigma tilde or something, 2n, which is the thing that propagates through. And now this picture looks very much like a cross-section, right? So it's like you have an entanglement wedge and there's some cross-section type thing which is propagating in the middle. So based on this sort of a calculation, Shinsei Ryu and his and Jonah, who's also my collaborator, they proposed that they just use this channel and describe this to be the answer, and that gives you something in holography which is related to the cross-section. It's a back-reacted version of the cross-section, but nevertheless, it's related to the cross-section. Okay, good.
So now this depends on whether n is even or not, right? Because
this depends. So this is the analytic continuation from even n. I mean, for getting the negativity, you want the even n. There's a similar calculation you can do for odd n, which was done in another paper. and then you get what's called the odd entropy. But you can do both, and both basically look like this.
So, sorry, what is the replicatory calculation of the negativity? Can you say?
So in simple terms, like the twist operators that we apply. So if you remember let me just say it in the permutation language. Maybe that's the simplest way to say it. So normally for the entropy, we would apply the permutation, which is
No, I'm interested in the limit, the log. That's your negativity, right?
That's the
Log
yeah.
on- so
Oh, you want
get
just
from this quantity?
which you want what n should be analytically
You
contributed.
want the
It becomes n equals a half, I think.
equals half
Yeah,
for even.
for even.
Even.
Yeah, so analytically continuing n equals half on the even one gives you this negativity. I mean, it's some maybe log of that or
Meaning
something.
you are taking it to be 2n and then n is going to half.
No, n is the so let's compute the even moments. So even moments of rho ABTP, this to the 2n will be sum over I mod lambda I transpose to the 2n.
Yeah.
And then n equals a half.
Okay.
Does that make sense?
Yeah.
Okay. Yeah. And whenever I'm talking about all of this, like we don't necessarily just care about the n equals half limit. Like we can talk about this at arbitrary n, and it's still a question. Like, what's the dual of that?
And working with odd n, is it useful at all?
It is useful. I mean, useful in what sense? Like, we don't know what the use of that quantity is. Like, it doesn't have a nice interpretation. Sorry.
This entanglement. We saw that negativity was useful.
Yeah. So in that sense, I don't think we know if it's useful. Like it's not, there's no LOCC property or something like that we know.
Okay.
It's not something that has been studied much. It was just motivated by, we know this even thing, why not try the odd thing? That's all. Yeah. Okay, good. So that's the naive thing you can write. Now, this seems like a very reasonable calculation. It's a very natural generalization of what Hartmann did for the entanglement entropy. So that gives you a saddle, which in the tensor network language looks like this. So in the tensor network language, what you're doing is applying some twist permutations on the boundary. So you're just tracing out C. So there's just identity that's acting on C. You're applying a cyclic permutation on A, which is called X here. And there's an anti-cyclic permutation that's acting because of the transpose, so because you're flipping everything. So that's X inverse. So cyclic is just going from 1 to 2 to 3 to 4, blah, blah, blah. And X inverse is going the opposite way. It's the opposite orientation. Good. So now, there was a calculation that was done. There was a random tensor network calculation that was done in this paper by Dongqi and Walter, which essentially showed that this naive saddle isn't the dominant saddle in the random tensor network. What ends up happening is that if you look at the Cayley diagram, then there are these elements X, X inverse, and identity. And there's actually an element in the middle, which we call tau. There's actually a class of elements, there's many such elements, which lies on the geodesic between all three of these. So if you look at the geodesic between X and X inverse, tau is on it. It's also on the geodesic between X inverse and identity, and also on, it's a very strange sort of thing, that it's on simultaneously on all of these lines. Okay. Now, what that means, so remember that in the tensor network calculation, what we were minimizing was the free energy, or it was the energy of some Ising model, right? Now, the energy cost just came from the brane, and in particular, it came from the tension of the brane was fixed by the Cayley distance. It was fixed by what the distance between the two different domains is. And so, just from the fact that it's a line, it tells you that if you had a brane between X and identity, inserting a small domain of tau doesn't harm you, because it saturates the triangle inequality, right? So the distance between tau and X plus the distance between tau and E is the same as the distance between E and X, because it's on a line. And the same is true for all of these combinations. So every brane can effectively be relaxed by adding a small tau domain.
Say that again, because what's confusing me is that even though they might, are you saying there are two geodesics that link at X and E?
There are many geodesics.
Many, but just because there are many, doesn't mean there's one, all of them have the same distance, right?
No, they do. I mean, otherwise they're not geodesic here means minimal. It doesn't mean extremal because this is just discrete.
Okay.
Yeah. Yeah.
So they all have the same distance.
Thank you. They all have the same distance, and this tau will lie. So there's many geodesics going from X to identity, and similarly from each of these. And there's a tau on which intersects. Like you can find it on a simultaneous geodesic. Like you can go from one to the other.
Tau is unique from many taus.
There's many taus actually. So what tau is I can just draw it. For the even case, tau is just pairwise contractions. Actually, there's even more, but these turn out to be the important ones for holography. So it's just pairwise contractions of elements. Just swaps. Sorry. Oh, this picture is like 1, 2, like the elements are labeled here. Sorry?
These are the replica.
The replica. So this goes from 1 to n.
Okay.
And the so it's just some permutation I'm drawing on this, and the permutation is the one which swaps 1 and 2, swaps 3 and 4, and so on.
Nice.
Yeah. So those are the specific. I mean, you can, yeah.
Sorry, so your conclusion was that the structures are like a project.
It's like it's this structure. Yeah. So because it's this structure, you can insert a small tau domain. So we start with the structure where this blue region didn't exist. But now we can just insert a small blue region, which is a tau domain, which can split open this cross-section type Saturn. Once you do that, now you're free to relax the branes. Now these branes are not necessarily in the minimal position, and they can relax down to the RT surfaces, because now they can open up. The X and X inverse domains don't have to meet any longer because the tau domain interpolates between them. And this is a replica symmetry breaking configuration. So tau is a replica symmetry breaking configuration. Right, you can see that it's not symmetric under Cn. So, in fact, in the random tensor network, you can explicitly show and prove that the dominant configuration is replica symmetry breaking for the analogous problem, for which in the CFT we believe that the answer is the cross section. So, here the answer is in fact related to the mutual information because it's a linear combination of all of these RT surfaces. So, it's some Renyi version of the mutual information.
And if you use this answer in gravity that you think is
this one,
this one that you think is likely wrong.
Yeah.
If you use that, what does the answer? What does the answer look like? The function of cross ratios.
It's you mean on the gravity side, right?
Yeah.
It is the cross section. It's like a back reacted version. It's the area of this surface which has some back reaction. So these you should think that the gravity dual of these is like you're inserting some cosmic branes on each of these surfaces, and it's the area of this surface in that back reacted solution.
I was just wondering if you took these two labels away.
If you take them away, then the problem is it'll get disconnected.
It
will sharply disconnect. So it'll go to this configuration, which has 0 cross section, so it becomes 0. So it's 0 at leading order. There's probably some quantum correction. But,
so it's non-zero up to some.
It's non-zero up to some finite cross ratio. I forget where the transition happened. Maybe it's at half.
Okay, fine.
Oh yeah, it should be symmetric. So yeah, I think it's at half.
Okay, fine. So it's non-zero up to somewhere.
Yeah.
And in that non-zero region, it's decaying with distance.
Yeah. So that's right. The value of this cross section. So let's say I just start from here and make the interval smaller and smaller. This cross section will start shrinking, and eventually at some point it just snaps. So it decreases and then jumps down to 0.
Okay.
Okay, good. So this is a concrete tensor network calculation. Now the question was, well, what about holography, right? So we'd like to know what the answer in general is in holography, whether replica symmetry is broken or not, and if so, what went wrong in this calculation and what else could we have done and so on.
Sorry, but the phase transition is at the same point that the phase transition for.
Yeah, I think it's because of symmetry, because
Okay.
The complement of 2 intervals is also 2 intervals, at least in 2D CFT.
Okay.
In higher dimensions, it's probably a more complicated function.
In the random tensor network case,
Yeah.
with this replica symmetric breaking saddle
Yeah.
now, was it possible to do some continuation where
Yeah.
it was hard to get?
Yeah. So this calculation did a very rigorous resolvent calculation, proved very explicitly that you can analytically continue, and you just get half the mutual information for the negativity.
And so, if you believe the random tensor answer in the large C limit, once again, there'll be a phase transition at the same point?
Yes, at least in 2D CFT.
So there will be a phase transition at the same point, but
it's this time it's like the mutual information, so it's continuous. Like the mutual information doesn't snap. This cross-section answer would have jumped discontinuously.
Okay, so the answer you're suggesting from the from the tensor network is much larger.
It's like order 1 over it's order central charge larger.
Okay, so should one somehow be able to physically argue which one's?
I don't know about that because there are physical, like the reflected entropy is a situation where like these discontinuous jumps happen, and you can prove that it happens. So maybe just.
I was wondering something like this. That sometimes there are bounds. If measures of mutual information die too fast, that means other things have to die fast. And you're saying that the gravity answer dies very fast compared to what you think is right. I was wondering if you could.
Die very fast, yeah.
I missed something. I thought gravity answer will go continuously.
So it depends. So the mutual. Let's not call it the gravity answer. Let's call it the mutual information answer and the cross-section answer.
Yeah.
The cross-section answer has a discontinuous jump, so it goes down, but then it jumps at some point to 0. The mutual information answer falls down to 0, and then it has a kink. It doesn't have a discontinuity. It just has a non-differentiability.
Wait, it isn't down to 0 as you're making points closer.
Further.
Okay, further. But okay, just go ahead. So you take these 2 points on top.
Yeah.
Further and further apart.
Yeah.
Initially, you are connecting.
Sorry, which are you making them further this way or that way?
You tell me what you're.
So what I want is to make the interval smaller. Like smaller means less correlation. Yeah.
Okay. That's what I originally thought.
Yeah.
Okay. So you bring them together, and initially they are connected like this.
Yeah.
And after that, there's a transition smooth.
Yeah. So if you believe if you believe the entanglement by cross section answer, then it was at a finite value.
Do you mind drawing a couple of graphs?
Okay. Then let's also Okay. I was just saying the mutual information. Okay.
So let's talk about the mutual information. So what the mutual information does is, if I look at it as a function of cross ratio, well, depends on which cross ratio. But okay, so there's some value half where it's z at leading order in C, it's finite. Maybe even infinite at some point, but whatever.
This is mutual. What are you?
I'm drawing the mutual information. So the mutual information goes down to 0 at some point and stays 0.
And I'm sorry for the x is as x increases, the 2 points above are coming closer or going apart.
The 0 is like when they have less correlation, so they're like for smaller intervals, which are further away from each other.
So the closer the intervals, the mutual information goes to 0.
Correct.
And now the naive.
And the naive answer would do something like this. I mean, I don't know if it crosses at some point, but basically it would go here and then jump down there. So there's a discontinuity in this.
And if you have two possible saddles, is the bigger answer preferred or the smaller answer preferred?
No. So firstly, there's some the smaller answer should be the answer. Let's see. Yeah, there's some. It depends on the analytic continuation a little bit because it's the subtlety that I talked about yesterday. Like naively, the brains have negative tension, so you may say that the bigger answer is preferred. But that's the wrong calculation for the Renyi entropy. So if you assumed like the tensions were positive, then it would want the smaller answer. That's basically what happens here.
I mean, I was just thinking if you compute two quantities, it's going to be this one or this one.
Yeah.
And then whichever is the larger one will be picked out.
At integer n, that's exactly the calculation, and then the smaller one gets picked.
Larger one. Oh, sorry. It's
smaller area, e to the minus area.
Okay, fine. Yes.
So the smaller one gets picked. But then it's a question of what's the rule for analytic continuation? Because if it's a negative tension, then you naively might think that you have to maximize the area, but that's the wrong answer in some situations. So I don't know. But at even integer n, you're right. It's the
smaller one. And so this graph then suggests that if this is the situation, you should pick the low guy.
Correct.
It's not like they're competing, right? This is just two different ways of doing it. You don't know which one is correct.
No, they're two different saddles. I mean, in this context, they're just.
In this context, this is some tensor network.
It's a tensor network calculation, but I think there's analogous gravitational saddles.
I mean, the fact that that dominance
And there's-
is clear because you see the first
Yeah,
picture,
exactly. It's just
not
relaxing
a-
the
it's
areas.
Not a geodesic.
Yeah,
Right.
yeah, exactly. I mean, roughly that's what I'm going to tell you also in gravity. But
No, but what I'm saying is that this calculation here is a CFT calculation.
yeah, so the CFT calculation, I don't know what the prescription is. If you do the gravity calculation, then there's
What
analogous
is
saddles
the
to this.
prescription in CFT calculation? I mean, you just take twist operators, you compute the correlator of those twist operators.
But it depends on how you analytically continue.
No, but you are arguing for even an integer else there is an
Even an integer n, yeah, okay, good. So
Not just
an
about
integer n also, I think that something similar happens, but I don't know how to extract that from the CFT answer. Like how to see that from some dominance of some channel.
Yeah, this is the part that I don't
Yeah, yeah.
And how is it that from a CFT answer can be different from this?
Yeah, this is something I'd like to know. I still don't know how to see it from the CFT side. What you can do is, instead of thinking of it as a correlation function of twist operators, you just think about it as computing the, I don't know, partition function on some Riemann surface, and then it's clear that this works because, I mean, we're just using gravity to compute that. So that definitely works. I don't know what goes wrong in thinking about it as a correlation function directly on the initial manifold that you care about. That's the thing I don't understand. I mean, I'd love to hear if you have ideas about it.
Maybe the lowest block doesn't.
The word?
The lowest block doesn't dominate.
Presumably that's what happens, but then the question becomes like, then is there a channel dominance at all? Like, how do you see that, and which channel is
Usually,
dominating?
you would believe that it dominates for some value of cross ratio.
Yeah, that's what this calculation was based on. So I totally
Not half and half, but somewhere else. Let's say.
I agree.
Yeah.
But here you can see that it's just never dominant. So
Let's see. I mean, I haven't yet seen the gravitation here.
sorry, but you believe the tensor network
Yes,
calculation?
yes.
Okay. Yeah.
So, sorry, I got lost. Let me just talk about the gravity calculation. And let me just talk about mutual information.
Good.
Right?
So none of this is gravity calculation.
Okay. Then, but those plots are not gravity calculations.
Well, this you can think of it as a CFT calculation, just a correlation function of twist operators. But I don't know how to get that. Sorry, but I don't know how to get the mutual information answer from this. So in that sense, it's a gravity calculation.
So what is the gravity? Next slide is gravity calculation.
Yeah, I mean the gravitational calculation is the analogous finding of a gravitational saddle with the replica boundary condition. So
Yeah.
that's the gravity calculation.
Right.
From that, we know how to get this, the mutual information answer, because it's just the topology that's given by this. But I don't know how to get it from the CFT because there's no channel which gives you this answer. So in that sense, it's a gravity
Okay,
calculation.
so let me just talk about the gravity calculation yet to come. Sorry.
Yeah.
Okay, but just to ask you, is there a jump like this in the gravity calculation? I mean, that
The actual gravity calculation,
Yeah.
I'll tell you, is actually this one.
so there is a jump.
No, there isn't a jump.
There is
It's
no
like
jump.
the mutual information.
Yeah, that's why I was very puzzled.
But,
okay,
but the
fine.
fact that a jump happens does happen in, like, say, the reflected entropy. So it's not like you could rule it out just based on that.
Go ahead.
So the reflected entropy is actually given by the cross section, and so it does have this jump.
Has a jump.
And so it's not like that's a bad. I mean, that does happen sometimes. It's not
That
like,
does happen.
Yeah.
But I was just trying to put it together that
Yeah.
if the random tensor network indicates that it should be a mutual information
Then it's continuous.
calculation, then on the gravity side, it seemed to me it would be continuous.
It is continuous.
Ergo, it should be continuous.
yes.
for-
The calculation is actually pretty analogous. Like the same thing happens here. Like
Okay.
even if you compute
Then
it,
at least, okay.
the cross section here, you'd draw the same pictures.
Okay, then I'm following at least the chain. Thank you.
Okay, good. So now let's talk about the gravity calculation. So also firstly I had said that these states, like the tensor network states, are basically fixed area states on the gravity side. So you can just reproduce the same calculation for fixed area states directly by the map that I told you before. So already this proves that in gravity, fixed area states have a negativity that's given by mutual information. So that's sorted. Now the question is, what happens for general states? Firstly, you could try to argue similar to what I was saying before, like you could use the answer for fixed area states, write general states in terms of a superposition over fixed area states and extract the answer from that. But then you need to somehow show that, like how the negativity of a linear superposition of objects behaves, and it doesn't necessarily behave in a nice way, unlike the entanglement entropy. The entanglement entropy has a nice linear behavior, so we could actually extract the answer for general states directly from fixed area states. The same thing doesn't work here. So first we rule that out. Now, what turns out to be useful about general states is actually there's a very trivial identity. It's something like an undergrad could have proved, like it was very trivial, but somehow it was missed all this while. And the identity relates the partially transposed density matrix to the thing that I told you about yesterday, which was the canonical purification. So remember that the canonical purification was defined as the state, which is rho AB to the n over 2 in the limit m goes to 1. Right? But now instead of m equals 1, I'll consider the state which is at m equals 2. Okay?
Yeah. Once can you define this MO? I know what the canonical purification is.
Yeah. So all we're doing is, so you start with the density matrix. So you start with the density matrix, take moments of the density matrix, so powers of the density matrix.
Yes.
And at the end, just convert all bras to kets.
All bras to kets. Got
So
it.
that gives you an entangled state, which was arrived at from the operator, which is rho to the n over 2.
Okay.
So
just as
in
you would do
particular,
for rho,
just as you would do for square root of rho, which was the thermofield double, like the canonical purification.
square root of rho. Okay, yes.
Right. But now, what I'm going to care about is the m equals 2 version of this. So it's just like rho AB. So just take rho and think of it as a state. It's just that state.
Correct, sir.
So good. So I'm just going to give you some diagrammatic picture for this. The diagrammatics is as follows. So rho AB has 2 bras and 2 kets, A and B, right? The partial transpose just flips the bras and kets on the B side. So that gives you this twisted thing, right?
Yes.
Now let's take rho AB transpose squared. So you just take 2 copies of this, glue them together, and you get this picture. Right, so all I've done is glued together this leg here, and we have these 2 open ends. So it's still an operator in the AB Hilbert space, which is obtained by multiplying 2 of these. Okay. Now let's consider the m equals 2 version of the canonical purification. So the operator rho was this thing. Now we can flip all the bras to kets and get this stop thing. Right? That's a state in this double Hilbert space. Right? With these extra legs on A star and B star. Now consider the density matrix, which are called sigma. It's just given by 2 copies of this, one in the bra and one in the ket.
Yes.
And now trace out the region A star and B. So tracing out A star glues this leg together, so you get something of this form, right? And tracing out B star removes this leg. Okay? Yeah. And now what you're left with is basically the same picture. You just straighten out this leg and you see that this leg is glued together. This picture is basically identical to this picture. It's just index contraction. And I'm just giving you a diagrammatic picture for a simple index contraction. So this is the same as rho transpose squared. Okay? So what we've done is related rho transpose squared to the density matrix on the canonical purification. But remember that yesterday we were considering the subregion AA star, but now we're considering the subregion AB star. That's the body.
Make sure.
Yeah.
So you related this rho AB transpose square
Yeah.
to the canonical purification.
Yeah.
And then traced over once again which
Traced
A
over
star and B.
A star and B.
B.
A star and B.
Yeah.
So it's like picking one of them from one and then the other one from the doubled version. Okay? So this is going to be a useful identity because when we're computing even moments of rho AB transpose, right? It's rho AB transpose to the 2n. We can instead write it as sigma AB star to the n. Right? So traces of this are sigma AB star to the n. So effectively now we have a Renyi entropy calculation. Once we write down what the state is for the canonical purification, all we're left with is computing the Renyi entropy in regions AB star. And it's a standard assumption for us to assume replica symmetry for that. So let me just be as conservative as possible and assume that that has replica symmetry, which is now a Zn replica symmetry, not a Z2n replica symmetry, right? And see what we get. Okay, good. So let's again consider this example of 2 intervals in the vacuum state. Okay. Yesterday I kind of argued to you that this is prepared by the torus path integral. So this is like a general fact. If you have 2 intervals, then the Riemann surface over which you compute the replica trig for index n is just genus n minus 1. So at n equals 2, in this case m equals 2, that's just a genus 1 object, which is the torus.
Yeah, because you have two cards.
You basically have two cuts. Like this is the picture. Yeah, exactly. So this is like the preparation of the bra, which has these two cuts, and then you have a ket, and then you just glue them together. So you have like a band and another band, and you glue them together, you get a torus. Okay, good. So now in this state, let's compute the entropy of AB star. Now the torus partition function is something we understand pretty well, right? We understand what this saddle is. This is basically just the BTC saddle. And in this picture, again, the inner circle is the double copy. So there's A star and B star, and the outer circle is A and B. C is in the other direction, which has been traced out. So C is in this bottom direction. Right? The two copies of C. So what we care about in the canonical purification is this red slice. It's the slice which you get by cutting open this donut. And now in this state, we're computing the entropy on A, B star. So firstly, let me remind you, if you computed the entropy on A star, what you'd end up with is two copies of the cross section. So this cross section is this blue line here and blue line here. Right? If you computed the entropy of A star, you just end up with that. Two copies of that. But now let's compute the entropy of A, B star. That is given by some surface which starts from these boundaries, and it's just some disconnected surface which anchors to A and B star. Now we can compare what is the so remember that we had a Z2n symmetry to start with, and we've only at this point assumed a Zn symmetry. So the only way that the full saddle is Z2n symmetric is if this saddle is Z2 symmetric. The Z2 symmetry that we're left to check is the one across this line. It's the one which swaps AA star with BB star. And that the only kinds of saddles which are Z2 symmetric are the ones which actually have branes that are sitting in the following way. The blue picture is like the cross section plus some horizon contribution. Right? You can think about this as a limiting case where so just think about just starting from this point and start from the endpoints of A and then go halfway to the cross section and then around. That's like a deformation of the green surface, right? And similarly, halfway this way and down and halfway this way is like a deformation of this surface. So already at near n equals 2, which is where this becomes tensionless, you can clearly see that the smaller surface is the ones which are the green surfaces, just by relaxation. This is basically the picture that I drew in the tensor network. That relaxation of branes was basically just this fact. And in fact, yeah.
So if I were to just work with the negativity, the replica trig,
Yeah.
with n equal to 2,
Yeah.
right? So that will give me some, that will presumably give me just the torus, right? Negativity replica trig. Is this give me torus?
At what n?
N equal to 2. That's the one that you are looking at, right?
What I'm looking at right now is looking at that state and then computing more. So there are like twist operator insertions at the endpoints of these. So I'm looking at this for arbitrary n.
I see.
I'm quotienting by the Zn symmetry that's left over. Yeah. Does that make sense?
Did the element tau also have this?
So exactly. So tau precisely has a Zn symmetry because now you're just flipping two of these, and that gives you the same picture. So tau also preserves the Zn symmetry, which was an important point. That's sort of the inspiration for just quotienting by that amount and then checking whether you have the remaining Z2 symmetry.
But can I, if I don't want to look at the general L, let's say,
Yeah.
What is the smallest? And I should look at n equal to 2.
Yeah, we can look at n equals 2.
So that would be some higher genus surface. But if you multifold by some Z2, then you get to this.
Yeah.
I see. And in this higher genus surface, it would be difficult to argue, I guess.
It's difficult to argue.
I mean, you're assuming kind of partially that.
Yeah, we're assuming partial replica symmetry, so that helps a lot. And that's pretty standard because that's what Lukowitz-Mandelsena taught.
That's what?
That's what Lukowitz-Madison taught us. Like we always do that. That simplifies life a lot. And in fact, you can argue that there is actually no.
But this is the Renyi entropy of the funny state, right?
This is the Renyi entropy of the funny state, which is equal to the even moments of the partially transposed density matrix, just by its side end. By the side end.
Okay.
Good. So actually, if you think about it, like even suppose you had a configuration which had branes in this blue locations, if you just undo the Zn, like if you just go back to the parent space, this isn't even a smooth geometry. Like there's no smooth geometry which has branes at intersecting angles when you have this Zn. Like typically you'll just have a locus which is a smooth, like one locus of it, which is like what the green surfaces are. So this sort of rules out any such saddle. And this is exactly what we found in the tensor network. So this is the analogous calculation to the tensor network, and this is pretty generic. Like the fact that these two surfaces don't preserve, like pretty much the only replica symmetric surface is the cross section, and we've argued now that, or at least that's the best Z2 symmetric surface, and we've argued that that doesn't work. So this is a pretty I mean, even though I only drew the two intervals example, this is a pretty general fact. So this I think is a reasonable evidence that actually replica symmetry is broken even in holography, in just the same way that it was broken in the tensor network, and the answer is hence related more to the mutual information. I mean, it's some function. I mean, similar. Like basically, when I say it's related to the mutual information, I just mean it's a function of the surfaces that are these minimal surfaces anchored to the intervals. It's some linear combination of those with back reaction and so on. But that's what I basically mean. But it's basically topologically the same as what we are doing.
That's what came out of the Torus calculus.
That's what came out of the Torus calculus. I mean, and I was just emphasizing that this is a pretty general fact. Like it's not just for the Torus, but you could argue more generally that this remnant Z2 symmetry that we didn't quotient by is actually not preserved generically for arbitrary states.
So more generally means what?
And not two intervals, like take some other example.
That would use homogeneous surfaces and so on.
It's true, but in the end, what you're arguing is just that, like in the end, the calculation just boils down to whether like this cross section is the minimal surface or whether you have like some relaxation of that.
Even in gravity,
In gravity. I mean, I agree that the picture is going to be harder to draw, but formally it's just the same argument. Okay. So that's basically what I wanted to say about the negativity, and so that this was the second application of tensor networks to the replica trick that I wanted to emphasize, and that's pretty much closing that topic. Okay.
but maybe I can ask more generally, like why is it that the CFT is like
Yeah, this is something that I still would like to understand. Like we don't have a description of replica symmetry breaking configurations directly from these twist operator correlation functions. I mean, at least I don't know of a way to see it. Like there is a way to see it once you maybe have like this full Riemann surface and then you're looking at the solution and so on. But you'd like to have a simple modification of Hartmann's calculation which reproduces this answer. And there's a very heuristic picture that we have, which I think in the end gives the right answer, but I don't know why it's right.
Okay.
Which is the following, which is maybe you can help me rigorize this. But what the rough picture is that instead of thinking about sigma n, you want to think about sigma n, like you want to break down the permutation into the Z2 symmetric part and the non-Z, like the remaining part. Right? So you want to think of this as a product of operators sort of, which are living close by, one here and one here, and think of that everywhere. And then it's just the usual vacuum dominance in that picture. Because now it's just that these contract with these contract with this contracts with this contracts with this, and you get the mutual information. Now the whole subtlety is in how you actually write it in the form of these two things, because naively
do it in the way that the vacuum dominates in all these contractions.
So it depends on like what's the step in going from the original calculation to this calculation. If you just write down if you just write down these operators just as like if I just take it out of a hat and tell you this is the calculation you want to do, then you can arrange for this to be vacuum dominant and it gives you this configuration. But the problem is like how do you space out these operators? Like they're pretty close. So naively you want to take the OP between them.
Yeah.
And
then you would have the sigma.
Yeah, so you can space them out a little bit and then it works out, but then, yeah.
Okay, but this is suggesting that, okay, so the way if you write 8 operators like that,
Yeah.
then you are using a channel that is presumably not dominant. While what you should do is collide those two first, right?
But so if we could rigorously write down the step which takes you from the original operator to this product of operators, then something like that is true. I don't know how to do
start
that.
with this.
Oh, start with this
And I
configuration.
ask you what is this answer. Now
Yeah.
you tell me this answer.
Yeah.
That will not
Okay.
be blindly correct. Right?
Yeah.
Because you would have to first collide those and then take this inside. So from this point of view, you can see what this, how you could get a wrong answer even from here. Because here you are kind of colliding wrong channels.
Sorry, which one is the wrong channel here?
The one that you just drew.
The mutual information one?
Yeah.
Why is that wrong?
Because they're far away there. They're far away there, right?
Yeah, but I think that
First
this
collide
picture
is-
is a little misleading in the
I'm saying
sense that.
start from this picture.
Yeah, but why is that the negativity?
When these operators come very close, then it's negativity. No?
It has like some OP, I mean, like, it'll have some extra conformal dimensions in front. Like, these two operators aren't such that, like, the sum of their operator dimensions is not the operator dimension of the negativity operator, like the original twist operator. So there's going to be extra factors in front which is controlled by the spacing, and it's like a divergent thing. I don't know how to regularize that. But I think this picture is a little bit, I mean, this OP can be a little bit confusing because you could have done this thing where on the Riemann surface itself, so what ends up happening, so let me just label this as 2n. So if you think of this as 2n, all of these are 2n. Forget about this one. Then it's basically that the outer operators are like sigma 2n and the inner operators, are like sigma n, sigma tilde, and this is some other sigma prime tilde, which is 2. So you can break up the calculation into first preparing the torus and then applying, I mean, it's basically the calculation I did here. Just prepare the torus and then apply the sigma n twist operators. That calculation is manifestly this. And so that has to work. But something goes wrong when you naively think of them as being close, because then you want to do the OP between them. But here they're like very distant, like
No,
the
but
twist operators are far away.
This is an opposite in some sense to your point of view, saying
Yeah.
how is it possible?
No, but this
that
is
we
an
might get it wrong?
identity.
It's because that you maybe
No, but this is an identity. Like
there are many things, right? Here you are preparing some state with some, this rho.
no. The fact that the negativity is computed by twist operators on a torus is an identity. I'm just rewriting the boundary path integral.
So say that again, what is the identity?
The Euclidean path integral that computes the moments of the negativity, it's computed on a Riemann surface, which you can think of as the torus with extra twist operator insertions. That's just a rewriting of
Achieve your transposition.
Yeah. The only thing I'm doing is instead of writing the full Riemann surface, I'm quotienting by Zn symmetry instead of Z2n, and I get this picture with the torus with extra twist operator insertions. And in that picture, it seems manifest that this is the right
I think
answer.
that discussion is not necessary.
Yeah, I don't think, already on the CFT, you could have done this calculation. But then the question is, how could you see that calculation from this original
It's very
picture?
sharp. It's
Sorry?
a very sharp question, right?
It's a very sharp question.
Yeah, how can this possibly?
Could you just say once again what the CFT question, original CFT question is? Just
So the
draw the
original
configuration.
CFT, where's the eraser?
Maybe you can use that way.
There should be a piece.
Plot is better.
Plot is better. The CFT question is, we started with a calculation which had 4 twist operators, which were this sigma 2n, sigma minus 2n, sigma minus 2n, sigma 2n. And we could take these operators to be reasonably close, such that, the channel you want to construct is that it's the one where these don't track. Now, this is just some 4-point function in the CFT at large C and in a holographic CFT.
Isn't this the same thing that arises in computing the 2n Renyi entropy?
It's not the same because of this. What's happened is normally, so that's what I was saying earlier. If this was a 2n and this was a minus 2n, that would be the same as the Renyi entropy. But because this is a flipped orientation because of the transpose. Basically, because of the transpose.
If you had that minus there, then any channel you will have identity.
Exactly. Like if you had the minus here, then this contraction is also identity. This is also identity. Everything's identity. But now it's not because if you do this contraction, there's an exchanged operator.
But in this channel, it's
in this channel, the answer is trivial. That's like the disconnected phase.
Okay.
So that one's fine.
Okay.
The question is, let's say you're in the connected phase, then how do you compute this 4-point function in a holographic CFT?
Okay, so those guys are nearer to each other. The side.
Yeah, let's say I'll draw it later.
Okay. And you say one way of doing it is just now make the covering Riemann surface?
Exactly. Make the covering Riemann surface, and in fact, like so you could do the full like 2n replica Riemann surface, but now I'm just choosing to also, let's say, just quotient by Zn. So I have a torus with Zn like operator insertions which are controlled by n instead of 2n, and that calculation is this calculation. It's the same as that calculation. So holographically, if we can compute it, we know what the answer is. It's related to this mutual information.
But just backing up just in the conformal field theory,
Just in
there is even without making any other assumption, there is
It's still
some 2n
Riemann surface
Riemann
where you can
surface
compute it.
with at a particular point in moduli space.
Yes.
So it's a very clear
It's a
computation.
very, very clear calculation.
Okay, there seems no confusion.
No confusion. This is just identical. Like, yeah.
It's what you
It's just rewriting what, yeah, exactly.
Okay, so then what was your confusion?
Yeah. So the confusion now, there's a way to, now you want to find a way to compute it, right?
Well, I mean, you mean because this is now some genus 2n surface or
Yeah, it's like a genus, some function of n surface. Yeah.
Okay.
Yeah.
And the problem is you don't know how to compute that high genus.
Function. Yeah. Like, let's say I just hand you a CFT, I tell you to compute this.
Okay.
That is the confusion.
No. So I'm not saying that's the sharp. I was getting to the sharp confusion. So that the normally the way that you would compute it is, let's say, use gravity, right? That's one way to compute it. Now in the gravity side, there's a very clear computation which tells you which channel. Like if you do this Zn replica symmetry quotienting, you get a torus with some twist operator insertions. That's again an identity. I mean, we're just writing it in different ways. And there, assuming Liuquet-Smilde works, we know what the answer is. Like it's just this saddle. So if you believe this, it's this saddle with these cosmic brains sitting at the green surfaces.
And once you continue to n equals 1.
Even at n equals 1, or like, I mean, assuming Liuquet-Smilde works.
Yeah.
Okay. Yeah.
Does Liuquet-Smilde really assert this would be the right saddle at every n?
Yeah, that's the assumption.
But it's probably not necessary, right? All they need is the analytic continuation to.
Yeah. Okay. Let's say n going to 1. N going to 1. This is the sharpest. So okay. Let's say. I mean, maybe you'll say there's an analytic continuation problem or something. I want to say that even at integer n, this is the right saddle, but we can say that.
Yeah.
So let's say n close to 1.
I mean, I'm not sure we really know that's the case for logic.
Fair enough. Fine. I mean, we don't know any counterexample, but I don't think. I mean, yeah, we don't necessarily know. Also on the tensor network side, we know, but whatever. Like it's doesn't matter. Okay, good. So now we have some way to calculate this using the torus partition function using gravity, right? So now we know what this answer is, and this answer can be thought of as doing vacuum dominance in a torus partition function, right? So you can think of these as probe operator insertions on the torus, which are contracting in the usual way, in the Renyi entropy way, like just in the identity channel.
Sorry, let's can you draw the torus with twist operator sensitive. So the torus, let me just say, Shiraz, the puzzle is that you can compute this 4-point function also in the way usually we compute 4-point functions in CFT, namely by OP, conformal decomposition.
And which channel is
These two contract, but then these two,
And that is the one that he's claiming is the right norm answer.
Yeah, so this one, so these two are both sigma minus 2n.
Yeah.
So that means the vacuum cannot propagate in the same channel. So there's some lowest twist operator which can propagate, and you get some diagram which is like
But large C,
which presumably sigma minus 4.
yeah.
Okay.
And that's the replica symmetric saddle. Like that, the gravity dual of that is the replica symmetric saddle, the fully replica symmetric saddle.
Okay, so if you assume that the lowest dimension operator,
Yeah,
and because of this large sequence,
exactly.
So that's sort of long for that now.
Yeah.
if you assume that,
Lowest dominance. Yeah.
okay, fine, I understand your problem.
So that's the naive sequence.
Just to understand, the puzzle is if you assume that, you get an answer which doesn't agree either with your tensor network
Or with gravity. Like let's just work at the level of
And,
gravity.
and now let me ask you this, a very nice question, which is, it seems to me, okay, but then forget it if it doesn't make sense. See, you are representing the action of these twist operators
Yeah.
as a way to show what is happening when you
In this
construct your
higher
Riemann
G-
surface.
yeah, that's
okay. All right. Now, and that is you can, given any Riemann surface with identifications,
Yeah.
I can map it purely deductively to some action of twist operators, right? Do you have a clear construction of the Riemann surface?
Yes.
So, is it that, when the two twist operators come close together,
Yeah.
I can achieve the same effective twist
Yeah.
by many permutation operators. If I'm outside a small region, the sigma 2n twist can be achieved in many different ways.
That's right. That's
So,
right.
if I were just a little away at least from the point where the operator is inserted,
Yeah.
I have many sort of KD paths to
In
obtain
the original picture, that's true, but then like the surface you'll construct will be very different if you change it, right? Like the topology will totally change.
But I was just wondering when they come close enough,
Yeah.
whether there is a way to break up the permutation.
That's exactly that.
Connect.
So that
Because
was
that's
my.
what it seems to be
Yeah.
coming out.
So that was my heuristic picture for this. That's what I
Okay,
was saying.
that
Like
was
we
your-
break it into
but-
these two operators and think about
But
it.
it might be possible to make it precise because any Riemann surface can be just deductively constructed in terms of the action of twists, I think. Okay, but I don't want to distract you guys. I mean,
Yeah. Okay.
you have a particular Riemann surface, I can always break it up into actual twists. And if you
Yeah.
have a Cayley path or whatever being followed in the
Yeah.
Riemann surface.
Maybe. Yeah. Okay.
All right, anyway, okay, go.
Okay. At this point,
Here
what-
we have all the experts.
One minute, if you don't mind. If we did the OP, just replace these guys by sigma minus 4n,
Oh yeah.
then that would be a sphere, right?
That would be a sphere?
Because it's the 2-point function of two twist operators. That Riemann surface would be a sphere.
Yeah.
Okay.
So you're replacing these or
I'm doing the OP. I'm replacing
just
it
the
by-
OP in this?
I'm replacing both by what you get from the leading OP. You get some minus 4n, 2-point function.
Yeah.
Okay. So then.
Yeah.
So your question about the puzzle about why this is failing, in Riemann surface language, is the question of why is it or is it not
That the
That
sphere
the
approximates this thing. Yeah.
the surface can be replaced.
Yeah. Exactly. That's one way to say it.
Okay.
Yeah.
So one can try to make it a geometrical question.
I think so. Yeah.
And cut that Riemann surface somehow.
Yes.
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 So somehow like this whole funny Riemann surface
Yeah.
is there's one patch of it.
Yes.
It's some operator.
Yes. Yes.
And okay, I don't have anything.
I think so. So I think this torus picture is kind of related to this because if I just draw this torus picture, that is a little hard to draw. I don't know how to draw a torus. Maybe that's the way to draw a torus.
And you draw eight points on that.
There's 4 points. There's 4 points
I thought
because
you-
they have different twists.
But you unwrap once.
I unwrapped
There's
once.
still 4 points.
There's
Yes,
still
sir,
4
yes.
points. So there's a twist operator here, twist operator here, twist operator here, twist operator here.
Let's label those ABCs.
Let's label
also.
it. So these are these. Let me label it as A, B, C, C.
No, the vertex operator positions also. Because I want to make sure that you are doing the OP that you are supposed to do later also. Because how can it be that the vacuum will dominate now?
Okay.
I think here, if you did the other OP, you would get the previous result, right?
If you did the sorry, which other OP?
If you did the that OP, continue to do this
Oh,
OP
this
that you're
lowest
supposed to
channel
do
OP.
there, then there is no reason.
Then you
why-
get this. That's right. Yeah.
Yeah,
this
so
is
then
one.
it's clear, right, that the OP is being done in a different way.
That's right. So let me just label them then. So it's 1, 2, 3, 4. Then what ends up happening here? So this region, this outer region I labeled was A. This is A star. This is B star. and this is B, right? So just the outer boundaries of these.
Isn't AB the bigger interval?
AB is the bigger.
No, AB is
What is AB?
the small. A and B are the small interval.
Oh, yeah. Sorry.
AB are
I wanted to say this. I wanted to say this. Yeah.
I want to see the entanglement between
You wanted the entanglement to be large. Um, okay, let me not read. Okay, let me just read it. 1, 2, 3, 4. Okay, thanks. So now the twist operators at the ends of A are 1, 2, and these are 3, 4. Wait, maybe I have to get the orientation right. 1 is close to 4. I think this is 4, and this is. I think this is what it is.
Yes.
And now the naive contraction is the one you said, which is there any color? The naive contraction is this one.
Yes.
And there's an exchanged operator which propagates along this.
Yes.
Something like that.
Yes.
And the actual correct thing is something that is like
No, why?
the bulk picture. That's the bulk picture. I'm saying on gravity, like there's a brain that's sitting at that location.
Why? Why?
So that's just
No,
minimal.
I'm saying it's a CFT person. Right? It's a CFT
Yeah.
person on a torus.
Yeah.
You have
Let's say we're at n close
Because
to
when
2.
you draw the bulk, you're assuming which cycle is to be filled.
I am, but
Mean that the other cycle is filled.
let's say that n is close to 1. It's a probe operator, okay? So if it's a probe operator, then you're basically just approximating it by the distances are all that matters, right?
Okay.
There's no back reaction.
Yes.
So now what I'm saying is the distance of this surface plus this surface, the other surface that I drew,
Yes.
is strictly smaller than the distance that you're drawing in the other channel.
Really?
Yeah, because that is just the blue surface.
Oh, sorry. The green surfaces are bigger than those small blue surfaces.
No, not just the small one. You have to include the cross section.
How can this be? I mean, as a CFT person also on the torus, there is continues to be the puzzle. I'm saying.
On the torus. You're saying what's the answer
Because
for this
1 and
torus
4 are
partition?
close. Yeah, 1 and 4 are close, right?
Well,
Just look
depends
at
on
here
the-
where it came from. 1 and 4 are very close.
they're close, but they have to also exchange this extra operator which travels around, right?
Yes.
That's the loss, I think.
No, but
I mean, in this thing, it's a trade-off, right? I mean, there's a trade-off with not having to travel that extra amount.
but now you are traveling twice while you travel once with the middle operator.
No, I don't think so. I think you are actually traveling twice. I mean, I'm not 100% sure how it works here, but in the brain picture, it's pretty clear that there's going to be a brain sitting there.
Half.
No, not half. It's on the whole thing. Because you're just computing the Renyi entropy here. Like you want to compute the entropy of both A and B star. So you need something that's homologous to that.
So possibly related slightly.
Yeah.
If you bring these two guys very close together and you look at the hygienous Riemann surface,
Yeah.
It'll have A cycles and B cycles,
Yes.
and one of the two cycles will become very small.
Yes. Yes.
In that limit,
Yeah.
only vacuum should propagate in the
relevant channel.
in the guy that's relatively long.
Yeah.
And
Yeah.
that sounds like the right approximation to me for evaluating that Riemann surface. Is that,
Yes.
can't we use that to just evaluate that?
That
But Shiraz, what if your operators that come close
are not
do not have
vacuum.
activity in their channel?
Yeah.
No, but now all I've done is replace that by some Riemann surface.
Yeah.
Now I have no more.
In that Riemann surface, I guess you just ask which is the contractible cycle.
Oh, the full
Riemann surface.
Now
So
I
I'm
have
just doing this partly, and I mean, one of the cycles we know, right? One of the cycles is just the torus, like the donut thing. And then the question is, what's the other? How do you relate it to
Yeah, so let me not do your Zn thing also.
Okay.
I just like the full guy.
Full guy.
Okay, so no
Yeah.
operators left.
Yeah.
The high genus.
Higher genus guy. It's a very symmetrical higher genus
Yes.
guy,
Yes.
right? So
It will have two G cycles which are very small
very
and G
small
cycles
cycles
that
which are very, very big.
Yes.
Okay, and now this OP limit is one in which the one which is very small. I would imagine, at least naively, that in that limit, in the guy that's big and long, only vacuum propagates.
Yeah.
And if we approximate the Riemann surface, that partition, then that you can compute, right?
That you can, you should be
Give
able
that
to compute.
approximation,
Yeah.
And then you get what you get.
Get what you get.
And
I feel like, but wouldn't that be the same approximation? Maybe that's what Abhijit is also saying. Like,
I think maybe, but please go on.
Wouldn't that, yeah. I feel like that'll give you the same approximation, but this picture
The same approximation as what?
as the naive saddle.
As the naive saddle. But then
Which was
why
this.
is it- why is
Yeah,
it
that's the thing. I don't know. I understand it in this picture, right? I don't understand what happens in the higher G. The higher.
No, but I mean, so I thought you said once you unfold,
Yeah.
even in CFT, you. Okay, but you say once you put gravity back in.
Yeah, you want to compute it in gravity. So.
And gravity is very good at.
Yeah, I know.
Facts.
Yeah.
Filling out the small things, right?
Yeah. So that's the thing. I think this.
So I feel like it would be a handle body with which is like a sphere with n punctures connected to sphere with n punctures with a very thin tubes filled out. So now it's just a spherical question.
Yeah.
Can we? Yeah.
And even just in the CFT, right? Couldn't you just compute this higher Riemann surface if you make this approximation? That only vacuum current here.
But when you cut, you just get a
Fine.
So that's like that.
It's like an.
So in that language, where does this sigma 4n come in?
That's about the violin. I mean the non-triviality.
No, but
from the violin. That I mean, finally there's a sphere, but
Yeah.
But you have to unwrap it n times to get actual sphere, and then go back and remove that conical excess. That's how you get the.
I see. So if what I'm saying here is correct, then you'd say that there must be some cycles where the vacuum is not dominating. Is that accurate?
It sort of sounds to me like that, right? And it would be odd.
It definitely is odd. I mean, at this sound, the original calculation sounds like a very reasonable calculation. So
No, but I'm wondering how much you can make here in the theorem.
yeah. I mean,
from the CFT side, right?
Yeah, I agree.
I mean, it seems like not even to care very much about large C. Because
If you're close enough, then
you can just.
Yeah, I mean, I guess, if you took the intervals close enough, then yeah.
Right.
This is just happening at some finite cross ratio because of large C, but whatever. Yeah.
Right, so I feel, in the.
it's like the trustworthiness.
Yes.
Finite
Yes.
So let's work with it, right? Directly the opinion.
Yeah.
I don't
Yeah, and
see
the
why
OP
it is
limit-
like-
Yeah.
I don't see.
Um,
So even in the torus picture,
Yeah.
if we those 1-4 are close, so I don't see how can that be. 1-4 are still close.
1-4 are pretty close.
I mean, again, going back to Shiraz's
Yeah, they're pretty
comment,
close.
when you go and follow the whole thing, it's narrow tubes that connect the sphere with them.
It sort of reminds me of the stuff we did was.
It's Schlenker.
Yeah.
What was that?
There were these papers that Witten did to try to argue that large N,
Ah, I see what you mean.
and he kept filling in narrow tubes.
Yeah.
That's all I remember about the papers.
Yeah.
But the reason I brought that up was there was a mathematician and there was a theorem.
I mean, especially in the OP limit, right? I mean,
I agree with you. I agree, but I'm still confused about.
Especially the
I
way you
do.
explained it, you could see how you could get the wrong one, right? Because if at this stage, if you start using a different channel, then
Correct. But do you actually, from the gravity side, I understand this, but do you understand why we need these two contributions in the twist exchange? That's the thing I don't know from the CFT side.
not to still say also one, right?
I mean, in
these
the gravity
two
side, we
close,
need both.
go like that.
That's the thing I'm confused about, because on the gravity side, it's clear that we need both.
Both.
Yeah, because is there any entropy of AB star, right?
Any entropy of A, B star.
So the thing that's homologous to it is the union of like this surface and this surface. That seems to be an important point, like because that's what's the trade-off. Yeah.
Maybe.
I mean, it's a very concrete question. I completely agree. Like, we should have a good answer for this.
It's
but
kind
yeah,
of
like,
a question I feel you could make a theorem on the same. I mean, I think some kind of thing you can be sure of.
Yeah. Yeah.
I mean, you were to guess.
Yeah. Okay. Yeah. That's useful. I mean, I guess we'll also. I mean, maybe what you're saying is like you can make a theorem in CFT without large C, but maybe at large C you'll need some assumptions of. Yeah.
It's possible
But-
that the small distance and large C don't appear.
Yeah. Yeah.
It's possible, but we don't have so much experience with that.
I don't know of any other example where that happens. So that's why I found this interesting.
You know,
Loss usually helps.
It helps. It helps. I mean, you can do it at finite trust ratio.
and you know, yeah, I was thinking even in gravity.
Yeah.
Once you put that thing,
Yeah.
and now it becomes a geometrical question in gravity.
Yeah.
This
Yeah.
higher genus physics.
Yes.
I think Schlenker had a theorem about when these things always wanting to fill up.
Uh-huh.
So I think even on that side you might be able to make a thing. You know,
Okay.
to get totally sure.
Okay. This is something actually we're trying to do, which is explicitly try to compute this torus example, because like there are these techniques to compute the action on the bulk side in 3D gravity using these handle bodies. You just see like explicitly the dominance of whatever channel we are saying versus this thing. But that's something we haven't done yet. But I agree it's a short.
Sorry for disruption.
No, that's fine. That's totally fine. Okay, great.
Let's check more about it.
Yeah, we should chat more about it. So now I very briefly just want to go back to the first talk and just talk a little bit. So we talked about the Euclidean description of these fixed area states, and I just want to talk a little bit about the Lorentzian description and some relations with tensor networks and the gap between holography and tensor networks. So one thing that's important in the story of fixed area states is what does fixed mean? So when we say fixed, naively we just think like a delta function, but really we want some smeared version of it where it has some finite width. So let me call that width delta AHRT, which is basically the standard deviation of the area fluctuations. And in gravity, it's possible to show that the conjugate variable to the area at the extremal surface is just the boost angle. So if you consider some extremal surface across 2 points, then the boost angle between these is what I'm calling S, and that's the conjugate. So acting with the area operator basically generates these boosts, single-sided boosts. And you can ask me more about this. This is something else that I've been working on. But basically, the uncertainty relation says that these two conjugate variables, the product of these widths should be larger than order G. Now, typical solutions that are prepared by smooth path integrals have both of these being order square root G. So that's like a coherent state, like where like in a coherent state, the width in the x and p is like square root h bar. This is basically the analog of that. Now, if we want to do a fixed area state calculation, then we basically need to take the widths to be smaller than this order of square root G, so that it's sharper and it has less area fluctuations. We're focusing on a smaller band. And you can choose this in different ways. So you can choose this to be some power of G, and depending on what power you pick, you get two kinds of states. So firstly, there are what we call pseudo eigenstates, which are when you take alpha to be greater than 1, you see that this ensures that delta S has to be parametrically large in G, so it has to blow up as G goes to 0, which means that there's no semi-classical description. The only valid description of such a state is as a superposition over different boost angles. Right? That's the only useful description. So it's like a superposition over semi-classical geometries. You have some data on the initial slice, but it doesn't have one semi-classical geometry describing it. On the other hand, you can also choose alpha to be between this window of half and 1, which ensures that you can still have delta S scaling down, so that let's say it's like G to the 1/4 or something like that, so that delta S still parametrically vanishes, and this is what we call squeezed states. So typically in harmonic oscillator, squeezed states are the ones where you reduce delta X or delta P and scale up the other one. And this is basically what we're calling the squeezed states version of fixed area states. This still ensures, like, since you have parametrically smaller fluctuations, at leading order at least, it's sufficient to guarantee that the Renyi spectrum is flat. So you could think of these also as states like the tensor network in the sense that it has this flat Rayleigh spectrum. But it still does have a good Lorentzian spacetime. So this is somewhere, if you look at the tensor network, the area fluctuations are actually exponentially small. They're very small. And so these kind of states are somewhere in between. They sort of interpolate between the tensor network-like description where you only have a superposition of the geometries versus the smooth states which were prepared with the smooth path integral. So,
yes. That went fast.
So
the area here, so if alpha was greater than 1,
alpha is greater than 1, then this delta S has to blow up, right? Because this side is order G. And that means that the uncertainty is infinite in the classical limit.
Uncertainty of
the boost angle. So the boost angle about the HRT surface. So if this is the HRT surface, the area of this HRT surface generates boosts on one side. That's the conjugate variable.
Okay.
And so you have large fluctuations in that, which is basically like saying if you have the two wedges, then there's a large time uncertainty between them.
So they sort of almost snaps.
It snaps, like so, yeah, exactly.
Okay, so fine. So it becomes very crazy.
It becomes very crazy.
Okay, and you said if alpha is between half and 1, why half?
Half was important because half is like the typical smooth state. That's the one which has like the fluctuations in a smoothly prepared state. It's basically like a coherent state. It's like order of square root G. And if you want something like a flat Rayleigh spectrum, which is related to what I was saying about the tensor network, then you want it to be at least smaller than that. Like it has to have smaller width than that.
I see.
To have a flat Rayleigh spectrum at leading order.
I think coherent state's not good enough.
Coherent states will have area fluctuation, so they'll not have a flat Rayleigh spectrum.
Okay.
So this is like a squeezed version of a coherent state where you're shrinking one of the widths and allowing the other one to grow a little bit. But still at the classic, I mean, still it has a good classical value.
Okay. For fixed area states, delta is very sharp, right?
So that's the thing. Like when I say fixed area states, it means all of this. Like I could be meaning any of these. Yeah, anything from no. So we can talk about both. Like that's why I'm trying to distinguish like fixed area states. Like you can think of pseudo eigenstates and squeeze states both as fixed area states. Like if fixed area states is just defined by the fact that the Rayleigh spectrum is flat or like the area fluctuations are suppressed by some amount, both of these can be called fixed area states. But specifically when I'm going to talk about, but one of them has a Lorentzian description, the other one just doesn't, except like as a superposition. And so now when I'm going to talk about the Lorentzian description, I'll just talk about half to one because they have.
So the more you localize the area, the bad the geometry. Right?
Exactly, because there's wilder fluctuations in the conjugate.
So alpha greater than 1 is like loop quadrature.
It's you can say that. I guess. I mean, one difference.
Space-time is not.
Space-time. Sorry, what is that?
Area is well defined, but space-time.
But space-time is not. Yeah, I guess you could say that.
That's what loop quadrature is.
Yeah. Yeah. Tensor networks are kind of like that. Yeah. So anyway, these half to one is basically something that interpolates between them. So you go from between these tensor network-like states and smooth states. Oh. So what does the Lorentzian spacetime look like? So if you remember, the fixed area state was prepared by some path integral where apart from the usual asymptotic boundary conditions, we had some conical defect that was inserted to prepare a state which has a definite value of the area. Now, we can now think about, so the state itself was, you can think about that source as a projector that's acting on the state, which is fixing the area to a particular value. So it's the source coming from that projector. And if you compute the norm, pi squared is just pi. And so the overlap is just computed by a path integral with this one insertion of pi, which is the conical defect. But if we want to understand the Lorentzian spacetime, what we want to compute is a correlation functions in the state.
Can you see that the pi is a projector? If you take two pi's geometrically, put them on top of each other,
yeah.
Is there a sense in which it's the same one?
I'm roughly going to say that. I mean, basically, you can take two pieces with these conical defects and fuse them and make one conical defect.
Right.
The size of the conical defect will change, but the area won't change. So you should think of the source as the area. I mean, yeah, it's fixing the area. So it just adjusts to whatever it needs to be. So if you want to compute correlation functions in this state, then you want to compute something of this form. So you have a psi O psi, which means you have projectors on either side now. Now you can't say pi square is pi because there's an O in between. And that's sort of the important point. So now what we want to do is really split open this path integral through the conical defect, have pi's on both sides, and then look at the semi-classical geometry that you get in between those two. That's this picture. So you have the usual asymptotic boundary. This is the yellow region, which you get in Euclidean space. And the blue region is the Lorentzian spacetime that you get in between the two defects, which are the projectors. And so this splitting was important because if you just do the naive analytic continuation, you end up with some complex geometry. Anyway, that's the wrong thing to do. The thing you should do is really think about these some limit where these two opening angles are just split, as you were saying, and inserting and just looking at an initial value slice in the middle of that by CPT conjugation symmetry. It has a real value for the induced metric and the extrinsic curvature. And so you get some real initial data to evolve, and then you just evolve this using the initial value formulation. So you get some Lorentzian space. That's sort of the picture. That's mostly what I wanted to say about this. There's other stuff, but you can ask me later. And finally, I wanted to comment on going beyond fixed area states. So we saw that there was some connection between random tensor networks and fixed area states. But an important point was when we considered fixed area states, areas in gravity are a more subtle thing than areas in the tensor network for the following reason. So whenever you have space-like separated HRT surfaces, they can be simultaneously fixed because these are space-like separated and they commute with each other.
One thing.
Yeah, I think right.
In a in the context of the supersymmetric black hole.
Yeah.
You have like sort of definite energies.
Yeah. Are these do these have two sides or they're just like a one-sided black hole?
Definitely, yeah.
Definite energy, right? Like there are energy eigenstates.
Yeah, what are you?
I would say definite energies, and I was wondering whether it's very big, but I was wondering whether there was something interesting to do with your fixed area.
Yeah. I'd like to understand this. I think this is a more general question, which is that like what do the like if you just take the limit. So let's say you took a bunch of those eigenstates and just grouped them together, so you have like at least.
But one of the great things is you don't need to group them.
You don't need to group them. But yeah.
Exactly, generous is we know exactly what the entropy is, and I was hoping you might be able to see some of that here.
So this is something I don't understand exactly. I mean, I don't know much about it, but do they all have good semi-classical descriptions?
Each state?
Each state?
Of course not.
Not, right?
No.
Okay, good. So do you get a semi-classical description if you take like a small band? That's sort of analogous.
You need enough states to make a
So
semi-classical.
let's say you have exponentially large number of states so that the entropy is still a classical thing.
Yeah, I would say even one, in angles, the energies are like integers.
Yeah.
You take even one integer, you'll have a good semi-classical description because it has e to the pi square states.
Yeah, so let's take one integer. What's the width in the energy there? It's parametrically small, right?
With the energy, but because
because of this even spacing is just effectively one.
Yeah, because it's just I'm talking really super small guys.
Yeah.
So all energies are integers.
Yeah.
EPS code.
So let's say you had a two-sided black hole like that. There's a similar relation, right? There's an energy time uncertainty. So the energy uncertainty will be related to the two-sided time correlations.
Yeah.
If you take the energy uncertainty to be pretty small, then you should see that there are large fluctuations in uncertainty in time.
Yeah, it's smallest n as string stuff. Yeah, basically everything becomes time independent in the sector.
Even two-sided correlation functions, like those should be time dependent, right?
Two-sided correlation should be time dependent, correct? But then anything that you can get by making BPS, right?
Yeah, I see.
I think should be completely time independent.
I see. But what's a space-time description of that? Like, let's say you wanted to compute a two-point function. it looks like there'll be, if it's a semi-classical description, it looks like there'll be two particles falling in and meeting. This doesn't seem like a time-independent thing.
Yeah, no, I highly recommend this Baldacena
Okay,
talk in 2020. This is exactly the kind of question
This is exactly the question.
addressed, right? He talked about how it excites the Schwartzian mode.
Yeah.
There's this long throat that's described by Schwartzian. And that it becomes some correlation function in this effective quantum mechanics of the Schwartzian theory.
I see, but in the end, the answer is that there is a semi-classical description?
Yes.
Okay.
Semi-classical.
But it's highly quantum because of this Schwartzian, or is it
It's quantum, but it's just one mode is quantum.
just one mode is quantum?
So it's everything.
So it's semi-classical.
It's anti-gravity, right?
Yeah. Okay, I see. So because you need like wild fluctuations in something, right? Like which should
There is
time.
at least one.
There's one mode which does
Yes.
that. I see. So it's classical except for that one.
Yeah.
Okay.
So I don't know what my question is, but I was wondering whether in that context you could say something about these fixed area states in some, with some precision.
That's a good idea. Yeah, I see.
Because fixed area states sound like there they will exactly pick out one charge, right?
Yes. Or like energy. Yeah.
Yeah, but in a very precise way.
Very precise way.
Not some band.
Yeah.
But very.
Yes.
And I was wondering whether.
Yeah.
So is fixed area state exactly the same then as? Well, it's what you said. This window. But you could make the window
Window small. Yeah.
That means this gravitational solution, this fixed area considered as supersymmetric.
Yeah, I mean, isn't it just microcanonical answer?
Yeah, fixing the energy is just microcanonical. So that's just
He has some other description.
No, but that's because classically the energy is the same as the area. Like classically there's no difference between them. So you can fix either the energy, or this was what I was saying in the first talk, which was microcanonical thermal field double is the same as the fixed area version of it at the classical level. But these are not the same quantum mechanically, and maybe that's where the difference. I mean, it would be interesting to understand like how to relate it to that.
Yeah. Anyway, you should go on. I just thought I would bring it up before I forgot.
But that's useful. Actually, there's a related thing which I maybe should mention, which is there's this double-scaled SYK, which is like a souped-up version of JT, right? Like it has some bulk description. This bulk description effectively is like a superposition over tensor networks. I mean, this chord diagrams business that Henry Lin has talked about is basically like having a tensor network in the bulk with some discretization scale. And that there's like a supersymmetric version of that, presumably. Like you can probably repeat all of Baldacena and Lin's story in that case, where it should have some tensor network description. And yeah, this is something I've been thinking about, but I don't know more that I can say right now.
Yeah.
Okay, good. So fixed area states have good. So sorry, what I was saying was, when you have space-like separated HRT surfaces, you can simultaneously fix them, right? Because these are commuting operators, and so you can simultaneously diagonalize them. Now, this is true for a family of nested regions. Suppose you have this region R1 and R2.
Let's say one last comment.
Yeah.
The nice thing about these supersymmetric theories is that one can do calculations using localization.
Yes.
So I wonder if somehow your fixed area states can interplay with localizations in that context to do something interesting. Maybe they show up in the localization as, often.
Oh, it's like singular solution.
Often localization happens because finally you have to do an integral. Maybe you're finally doing an integral over some fixed area states. And I mean, just stupid and wild.
Okay, I probably have to learn more about that.
No, I say all this because this is really cool, but it would be nice to find context where it's very,
I agree.
unshakable.
Yes, yeah, I totally agree. I mean, that's sort of where I wanted to go.
Yeah.
Okay, good. So let's say you have space like, nested regions like R1 and R2, so where R1 is strictly contained in R2, then the HRT surfaces are just contained. I mean, they're space-like separated because they're just nested, right? But if you have regions which have overlaps, but they're not contained in each other, like R3 and R1, then their HRT surfaces will generically cross, and in fact, in time-dependent situations, they'll be time-like separated generically, right? So these are not operators you can simultaneously diagonalize. And this is pointed out in this paper where they discuss this in context of tensor networks. For time-independent geometries, it's fine. You can put everything on the same slice and all of that. But in general, you can't even put these two operators on the same slice, they'll be time like separated, so there's no sense in which you can simultaneously fix both of them. Or you have to, yeah. But somehow the random tensor network actually does more, right? The random tensor network has flat spectrum for any subregion that you choose. That's more than what gravity can do. So that this is sort of a place where the random tensor networks, even though they're related to fixed area states, cannot simultaneously understand all of the subregions. That's sort of a shortcoming, right? Like even with fixed area states, you cannot explain this.
I thought that wouldn't the conclusion then be the random tensor networks are good descriptions of time effects?
You could say that, but the fixed area states can do a little bit more. So suppose you just had a tensor network which is like a chain of tensors, where all the surfaces are just space-like separated from each other. You don't need to assume that this models a time-independent geometry. It could model a time-dependent geometry, just that these are space-like separated surfaces. So the fixed area state tensor network correction can go beyond time-independent geometries. So yeah, and this isn't a problem for time-independent geometries. So that's definitely true. But let's say you wanted to go beyond. Okay, so what you can do, and this is some work in progress, is instead think about what are called constrained HRT surfaces. So instead of, so we know that gamma R1 and R2 are time-like separated, so their areas don't commute with each other. But instead consider what's called a constrained HRT surface. This constrained HRT surface is, so let's say we first fix gamma R2, and then we look for a surface which is anchored to R1, which is extremal, but it's with the constraint that it intersects gamma R2 somewhere. Now these are guaranteed to be space-like separated. But now what ends up happening is this, this constrained HRT surface, which is gamma R1/R2, is only extremal everywhere except this meeting point. At the meeting point, it can have a kink, just to adjust this. Nevertheless, because it's space-like separated, this guarantees that these two operators can commute. And we can now construct like a network using such a family of surfaces. So if you interpret the random tensor network as constructing a network of constrained HRT surfaces, then you don't run into this issue of whether it's computing the which area is being fixed, because you can simultaneously fix all of those areas, right? Okay.
So this
Yeah.
is intersecting at a particular point.
Yeah, I'm just putting, so the way it's found is you're going to find the minimal surface, which is, I mean, it's extremal everywhere, except it's intersecting somewhere on the green surface, and it'll just find that point. Like it'll find some point and there'll be a kink at that point. Okay, so
Is it symmetric?
it's not necessarily symmetric. Like for example, this surface would be very close to this. It doesn't need to be symmetric. The picture is probably a little bit later.
No, I mean it's symmetric in the green and the blue.
It's not symmetric in the green and blue because, like for example, the blue surface, the actual HRT surface for R1 is this dark blue surface which passes underneath. So if you had gamma R2/R1, it would intersect with that surface.
Then it intersects, it will also pull it, right? It will destroy the extremality of R2 also. Or
No. Here we're just talking about the surfaces, no back reaction or anything. So that it's not symmetric.
Yeah.
Okay. Good. So now we were thinking about giving it an entropic interpretation. So is there a situation where instead of HRT surfaces, you have these constrained HRT surfaces which are relevant for some entropic calculation? And the situation that we thought of was the following, which is, let's say you had a fixed area state of gamma R2. So that's what we fixed here. Which is the green surface. I'm just drawing the transverse directions now. So the green dot here is the extremal surface, gamma R2. Now the constrained HRT surface is this light blue surface, which is anchored to the boundaries which are R1, and then it's just extremal everywhere except it has an intersection with the green surface. Whereas the actual HRT surface is something like the dark blue surface. Now let's say you consider a fixed area state of gamma R2, which now I'm taking to be a pseudo eigenstate. So it's something which doesn't have a description in one spacetime, it's actually a superposition over spacetimes. When it has a superposition, where it's a superposition of varying boost angle, right? So the conjugate variable was this boost angle. So it's a superposition with different values of the boost angle, which are sort of a roughly equal superposition of different boost angles. That's what a fixed area state is. I mean, a highly fixed area state. Now you can compute the entropy, like each of those individual spacetimes is a semi-classical spacetime. So you can compute the entropy there using Lucas-Marlesena and obtain the answer, which is the HRT surface. So you get e to the minus n minus 1 times area of the HRT surface. But you're summing over all of these, and so it's going to be, the answer is going to be dominated by the one which is the smallest area. And you can show by a maxi-min argument that the smallest area surface is actually the one where the boost angle is 0, right? Like it's the one which is the symmetric one, where you essentially start with the constrained HRT surface and unfold it all the way down. The flat surface is the smallest area surface. And all of these surfaces, just by maxi-min argument, can be shown to be larger. Which means that the saddle point in the sum will come from the constrained HRT surface. There's a particular spacetime where the constrained HRT surface is the HRT surface. They just happen to meet. And so, and there's some technicalities that, I mean, you want this to not back react, so you need to take n to be 1 plus epsilon, but you can't take epsilon to scale with g, so it's technically not the entanglement entropy. But nevertheless, small n near 1 Renyi entropies are actually given in a fixed area state of gamma R2, are actually given by the constrained HRT surface, by the area of the constrained HRT surface. So that's, I mean, so this is something which we've been thinking about, which is how to go beyond just the time independent situation. You can have some time dependent networks, but interpreting it slightly differently. Instead of RT surfaces, we think of it as these constrained HRT surfaces. So good. So let me just try to summarize with that. I tried to argue that fixed area states were a useful basis for some purposes, especially with the replica trick. Depending on the area width, they interpolate between tensor network-like states and these smooth semi-classical geometries. The random tensor network provided a useful toy model for the replica trick, and we saw two examples, which were the reflected entropy and the entanglement negativity. Both of which, in both of which we learned something about the replica trick in holography by using the simpler replica trick in random tensor networks, and the fact that we can think of random tensor networks as simultaneously fixing all areas just by interpreting the network in terms of constrained HRT surfaces. So this is sort of a toy picture for it, where you first fix a family of green surfaces, which are all space-like separated, and then you span the other direction by looking at constrained HRT surfaces, which are extremal everywhere, except they have like these kink meeting points. And that's sort of a more refined version of the bulk geometry. So this is a slight generalization of what we said before. And now finally, let me show you something that you guys have not seen so far, which is a thank you slide.
I guess there have been plenty first. Yeah. But in Zoom, yeah.
I don't think anyone's left on Zoom. I think is Gautam? No, I don't think anyone's.
Just one very brief question. I'm trying to think back to your first lecture with your fixed area states.
Yeah.
So you had you tried to fix the area of this extremal extremal surface, and you did that by putting these Lagrange multipliers and so on. Now, and that gave you a classically well-defined problem.
Yeah.
Now, of course, this is a useful trick for classical or semi-classical gravity, as we discussed. The question of whether you can go beyond classical gravity came up then. I wonder whether you've, in that context, you've thought about trying to see whether you could define an analog of what you're saying on a string word sheet. It's probably way out, but just
yeah, a fixed area
or fixed whatever.
fixed length or something.
Or fixed, I was thinking wall length, whatever, wall.
On the string word sheet, you mean?
Meaning,
not the,
you're computing a path integral with an insertion of this thing. Typically, path integrals are some partition function on some sigma model. Is there something we could link to the sigma model too?
I see. So you're fixing some like target space, like there's some target space source.
Meaning, you're getting some sort of conical deficit.
In the target space, let me know.
In the target space. Conical deficits in string theory by themselves don't usually make sense. Zn orbifolds
makes sense.
It's very vague and probably way out of reach, but I just was wondering whether you had any thoughts.
I haven't thought about this at all actually. This is
No, that's just a stupid question. Sorry.
No. I mean, I think
I mean, are you hopeful that it will make sense more generally, or it's
I
just
feel
some
like
sort of...
I think it should make sense. I don't think it'll make sense. I don't believe it will make sense non-perturbatively at the full quantum level. I don't think there's any reason to believe that. But I think
classical string theory.
At least in classical string theory, I feel like it should make sense.
Okay.
Then I think large n should be sufficient. Like,
is there a question even for BTZ black holes?
I
mean, so we can look at these fixed area states in ADS3.
Yeah.
Okay, so then at least the BTZ black hole, we know what it is as a conformity theory.
Yes.
So you do this, you turn on a little bit of your source for the area. That should deform it. Only in a small way. So is that a prediction that there exists a two-dimensional conformal field theory which is a small?
That seems like a prediction.
What could that be? I mean, okay, these are kind of things.
CFT which have
but I'm not sure if it's a 2D CFT, but let's say it's a 2D CFT which puts a small deficit angle at the center of the
state in the CFT.
No,
it's a deformed background.
The 2D CFT corresponds to this new bulk geometry. Bulk geometry is in the bulk there is a.
Right, so that's about the state, right?
But it's some path integral. I mean, he wanted to compute a path integral by fixing the size of the external surface. Space-time path. So every space-time path integral I thought would be the expectation value of some partition function of a 2D CFT.
But in particular in that CFT you can consider any state, right? State.
I thought it would just be the partition function of that CFT. Some new CFT.
The CFT being a world sheet CFT.
Oh,
that's the important. Yes, it's just changing the background.
You're thinking,
not the target space. Yes, exactly.
Now maybe only the full thing. I mean, your path integral was also performing the integral over the Lagrange multiplier.
Yes.
The source geometry came at a particular value of that.
Yes. But you can probably integrate over CFTs or something.
Maybe it's only the full thing that's some CFT. I don't know. I just wondering.
This is definitely not something I've thought about. One thing I have thought about a little bit is trying to go beyond the semi-classical level. For example, we have situations where we understand the path integral, right? Like in JT gravity, for example. And you could ask, forget about the saddle point approximation. Can we talk about the fixed area path as a path integral itself? Integrating over off-shell geometries, and it turns out to be pretty complicated. Pure JT is kind of simple. It's not simple. Actually, even pure JT is complicated. At least I have not made any progress. But it feels like a thing. Like if it exists to some, at least in an asymptotic expansion or something like that, then we should be able to make sense of it.
There were these bold papers of Atish Dabholkar, where he tried to do black hole thermodynamics in this way. Take a string world sheet, put an orbifold at the center.
Is this like the Susskind-Uglum sort of thing?
I don't know. Maybe.
I mean, they also had some story like this where it was the sphere partition function on this deformed background with a defect.
So it must be. Must be. But Atish is probably later. So if it's like that, he incorporated, and it's sort of fed into the more recent discussions of entanglement entropy.
Yes.
all of those discussions vaguely reminded me of your fixed areas. States. That was all.
Yeah, actually, this is probably a bigger question. So, firstly, in fixed area states, what the natural thing to consider in Einstein gravity, the higher derivative version considered the geometric entropy, like the long entropy. So, you could probably ask in a full string theory, like, what's the right thing to even consider? Like, I don't know what's the analog of the RT formula for string theory. So, that's probably the first thing to understand.
No, but there are two questions. You see, the hard question, a question that's
I see.
irritating and has been around for a long time, is how do you use the string world sheet to compute thermodynamic quantities? Like air. You know, there's no confusion about the world sheet. So let's say it's the BTZ black hole.
Yes.
But how do you use it to compute, say, the free energy?
Yes.
That is one question which is irritating and old and has to do with some IR issues. Right, because it's the IR, it's in gravity you measure free energies or energies at the IR end of the space. This world sheet is non-compact. There's some IR issue there which is old and irritating and we've discussed a lot and we don't know how to solve. But there's another question, which is because you're deforming the space
defect.
So without computing its free energy, you could ask, does there exist such a solution?
Okay, yeah.
And I feel they're slightly different.
I see.
And this may be a little more practical because people haven't thought about it.
So it's just like some solution which has a conical defect and the right
and it should be some 2D reactive at least after something. It should be something good, right? It's probably completely stupid.
Actually, sorry, the all-before's probably exist, right? So at even whatever when the specific values of the conical defect, these backgrounds do exist, right?
Yeah.
And it's a question of okay.
Now orbifolds exist, but they're typically tachyonic. You know, there are all issues. Okay,
I see.
What's the mistake?
Well, that's the first question. You know, C2 on Zn is supersymmetric and so has no tachyon. The C on Zn, which is what this thing will give you, right? Typically has a tachyon, and the endpoint of tachyon condensation is it removes the twist. I mean, it removes the Z. Smooths out. Cool.
Okay. Oh, that's actually useful.
Okay, thank you. Sorry for.
No, that's very nice suggestion.
That's fine.
Thank you so much. Thanks for